Okay, what you're seeing right here, this might look like something straight out of science fiction, but it's not. This is the blueprint for a real concept, a nuclear electric starship. It's a revolutionary type of spacecraft that could finally unlock the farthest, most mysterious corners of our solar system. So in this explainer, we're going to break down exactly how this incredible machine is supposed to work.
All right, so let's start with the big question. Why is it so incredibly difficult to explore the outer planets? I mean, missions to places like Jupiter or Saturn can take years, sometimes even decades. And the probes we send are, well, they're tiny. And this isn't because we lack ambition, it's a deep-rooted problem of physics and engineering that has had scientists scratching their heads for a very long time.
And this, right here, shows you the just mind-boggling leap in scale we're talking about. On the left, you've got a typical probe from the past, something like Deep Space One. It weighs about 500 kilograms, that's like a grand piano, and has a couple of kilowatts of power. But on the right, this new concept is up to 100 times more massive and generates well over 100 times more power. This is not just an upgrade, folks, it's a whole new class of vessel for exploration.
So, you've got this giant ship. How in the world do you power a beast like this, especially when you're hundreds of millions of miles away from the sun? Well, that brings us to the first huge piece of the puzzle, the power core.
And this is where you run into the really tough engineering challenge. Take a look at this. The actual science payload, the instruments, the cameras, the entire reason for the mission, is only about 5% of the ship's dry mass. Almost everything else is just for power and propulsion. And then you have to add all the fuel on top of that. It's the tyranny of the rocket equation in action, and it's a brutal master. This is exactly why a super dense, super efficient energy source isn't just a nice feature. It's the only way missions like this ever get off the drawing board.
The solution, though, is pretty brilliant. It's a hybrid system. At the very heart of the spacecraft is a compact nuclear fission reactor. This thing just hums along, providing a massive, steady stream of power for decades at a time. But when the ship is closer to the sun, say near Earth or Mars, these huge solar arrays unfold to give it an extra jolt of power. What you get is the best of both worlds. Constant, reliable energy way out in deep space, plus a backup system for extra safety.
Okay, so you've got all this incredible power, but that's useless if you can't actually turn it into motion, right? So let's head over to the engine room and talk about the hyper-efficient engines you need to push a ship this massive across the entire solar system. Now, before we can really dig into the different engines, there's one key term we gotta wrap our heads around: specific impulse, or ISP for short. The absolute simplest way to think about it is like a car's miles per gallon. A higher ISP just means you get way more push out of the same amount of fuel. And for these super long missions where every single kilogram counts, that is absolutely critical.
So here's a quick look at the main players. On one end of the spectrum, you have chemical rockets, like the ones on the space shuttle. They have incredible thrust, just raw, brute force, but they are terrible on gas, with a really low ISP. Then way over on the other extreme, you have things like ion thrusters. Their push is incredibly gentle, like it wouldn't even move a piece of paper on your desk. But their fuel efficiency is just completely off the charts. You see, it's all about trade-offs. I mean, just look at this chart for a second. The difference is staggering. A chemical rocket gets an ISP of maybe 450. A nuclear thermal engine can double that, which is pretty good. But an ion thruster, we're talking 10, even 15 times the fuel efficiency. For a multi-year journey to the outer planets, that's not just an improvement, that is a complete game changer.
So that begs the question, right? Why not just slap the most efficient engine on there and call it a day? Well, it all comes down to this trade-off. The high-thrust engines are like drag racers. They give you a massive, super fast burn that's perfect for something like breaking out of Earth's gravity. But those high-efficiency engines, they're the hypermilers of the rocket world. They give a gentle, continuous push for months or even years at a time, and over that long haul, they build up tremendous speed using just a tiny sip of fuel. This ship is designed to be smart and use both.
All right, we've got our power core, we've got our engine. Now let's put it all together. Let's look at the blueprint for this thing. How do you actually assemble a structure this big and this complicated? And more importantly, how do you make sure it survives the incredibly harsh environment of deep space?
And the design they came up with is so elegant because it's so simple. It's basically a dumbbell shape. And here's the genius of it. You take your powerhouse, the nuclear reactor and its heavy radiation shield, and you stick it way out on one end. Then you connect it with a super long but lightweight boom to create as much distance as possible. And way out on the other end, that's where you put the brains of the operation. All the sensitive science instruments, the computers, all safe and sound, far away from the reactor's radiation. And just to give you a sense of the sheer scale we're dealing with, a nuclear reactor kicks out a ton of waste heat, and you have to get rid of it. To do that, a ship like this would need about 422 square meters of radiators. To put that in perspective, that is almost the size of a professional basketball court, just bolted to the side of the spacecraft to keep it cool. Incredible.
Now, you can't just build this thing out of stuff you find at a hardware store. It requires a whole suite of advanced, almost exotic materials, and each one is picked for a very specific job. The main structure uses lightweight composites to save every possible gram of mass. Key stress points are reinforced with super strong titanium alloys, and the parts that get incredibly hot, like the reactor and those radiators we just talked about, they're built from these amazing refractory alloys. Every single piece is a marvel of material science.
Okay, so we've talked about this incredibly complex, powerful, just amazing machine. But it all comes down to one question. Why? Why go to all this trouble? What's the ultimate payoff?
You know, there's a quote from the original design study that just nails it perfectly. It says that combining these systems yields a spacecraft capable of ambitious robotics exploration, enabling missions far beyond what conventional probes can achieve. It's not just about building a bigger ship, it's about fundamentally changing what's possible.
So what does that actually let us do? What does it look like in practice? Well, it means we can finally stop thinking about just doing quick flybys. With this kind of technology, we could send massive, fully equipped robotic laboratories to places like the icy moons of Jupiter. We could actually go into orbit around them for years, studying them up close, and maybe even deploy landers or rovers to go down and explore the surface directly.
Look, this is the crucial point, the main takeaway. This isn't just a slightly better version of what we have now. It's a fundamental shift. We can carry way more science equipment, and we can get it to the outer planets in a fraction of the time it takes today. The bottom line is simple. It means more science, faster.
And that really leaves us with one final incredible question to think about. If this technology basically hands us the keys to the entire solar system, if we could build one of these massive, fully loaded labs and send it anywhere we wanted, where do we go first? The possibilities are just extraordinary.